Einstein's reluctance and the Schwarzschild solution. You think Einstein figured out black holes? He didn't. He couldn't stand them. 1916, World War I, the Russian front, trenches, artillery, death everywhere. And Karl Schwarzschild, a German physicist serving as an artillery officer, is solving Einstein's field equations, not approximate solutions, not simplified versions. Exact solutions. The first exact solution to Einstein's theory of general relativity. Think about that for a second. Einstein publishes General Relativity in November 1915. Revolutionary, beautiful. The equations that describe how mass curves space-time, how gravity works. But they're brutal. Nonlinear partial differential equations that nobody thought could be solved exactly. Einstein himself didn't solve them exactly. He used approximations. Schwarzschild gets Einstein's paper. He's in a war zone. He's dealing with ballistic trajectories, military calculations, and in his spare time, he solves Einstein's equations exactly for a spherically symmetric, non-rotating mass. December 1915, 1 month after Einstein's publication, Schwarzschild sends his solution to Einstein. Einstein is thrilled. He presents Schwarzschild's work to the Prussian Academy. He's impressed, genuinely impressed. Finally, someone's actually solved the equations. But there's something in that solution, something strange. Two places where the math breaks down, where the equations blow up to infinity. We call them singularities. One singularity at the center, R chakra 0, the very center of the mass. Okay, maybe that makes sense. Infinite density at a point. Weird, but perhaps just a mathematical artifact. But there's another one. At a specific radius. For a mass m, it occurs at r or 2gm c2. This is what we now call the Schwarzschild radius. At this radius, something very weird happens in the math. Time appears to stop, space appears to flip. The solution breaks down. We now call this the event horizon, the point of no return around a black hole. Schwarzschild didn't live to see what his solution meant. He contracted a blistering skin disease on the Eastern Front, pemphigus, and died in May 1916, just months after his discovery. He was 42. Einstein was left with this solution, this exact, beautiful, disturbing solution, and he hated it. Not the math was fine. What he hated was what it implied. See, Einstein thought the singularities were unphysical, mathematical curiosities that wouldn't appear in nature. The central singularity? Fine, maybe that's just saying you can't compress matter to a point. Nature probably prevents that somehow. But the event horizon, that bothered him more. Einstein spent years trying to convince himself and others that black holes couldn't form in the real universe. 1939, Einstein publishes a paper. The title is almost offensive. On a stationary system with spherical symmetry consisting of many gravitating masses. His argument, rotating matter would never collapse densely enough to form an event horizon. The centrifugal force from rotation would prevent it. Matter would reach some minimum radius and stabilize. No event horizon, no black hole. Problem solved. He wasn't alone in this discomfort. Most physicists at the time agreed with him. Arthur Eddington, the British physicist who helped confirm general relativity during the 1919 solar eclipse, said there should be a law of nature preventing stars from collapsing to the Schwarzschild radius. He called it repugnant that a star could shrink to that point. Why were they so uncomfortable? Because black holes break everything we think we know about observing the universe. At the event horizon, time, as measured by a distant observer, stops. Light emitted from the surface gets infinitely redshifted. You can't see past it. You can't get information from beyond it. It's a one-way door in space-time. Worse, the central singularity, a place where density becomes infinite, where space-time curvature becomes infinite, where the laws of physics, Einstein's own laws, break down completely. Einstein built a theory that predicts its own failure, and he couldn't accept that. So he did what any physicist would do when faced with an uncomfortable prediction from their own theory. He looked for reasons it wouldn't happen in practice. But here's the thing, Einstein was wrong. Nature doesn't care about our comfort. Nature doesn't care if we find something repugnant. The universe makes black holes. It makes them from collapsed stars. It makes them from the deaths of massive suns. It makes them at the centers of galaxies. Supermassive black holes millions or billions of times the mass of our sun. We've observed them. We've detected gravitational waves from black holes colliding and merging. We've photographed the event horizon of M87C, a supermassive black hole 55 million light years away. Black holes are real. But Einstein never knew this. He died in 1955, still uncomfortable with the implications of Schwarzschild's solution, still believing nature would find a way to avoid them. He never had to confront what black holes actually mean. He never had to grapple with the deep questions they raise. And that meant there were things about black holes, profound things, disturbing things that Einstein never discovered. Things that would take a different kind of physicist. Someone who didn't share Einstein's discomfort with quantum mechanics. Someone who was willing to ask what really happens at the edge of a black hole. Someone like Feynman. The information problem Einstein never considered Einstein died in 1955. April 18th, 1955 to be exact. Princeton Hospital, he was 76. An abdominal aortic aneurysm. He refused surgery. He'd lived long enough, he said. He wanted to go when he wanted to go. He died before the term black hole even existed. Think about that. The man whose equations predicted them never heard them called by that name. John Wheeler coined the term black hole in 1967, 12 years after Einstein's death. Before that, they were called frozen stars or collapsed objects or Schwarzschild singularities. Awkward names for something people weren't even sure existed. But here's what matters. Einstein never had to confront the deepest problem black holes create. The information problem. Let me make this concrete. You take a book, a specific book, and let's say it's a copy of Shakespeare's complete works. Every word, every letter, every punctuation mark, that's information. A specific arrangement of atoms encoding specific meaning. Now you throw that book into a black hole. What happens to the information? You might say, well, it's gone. It fell past the event horizon. It's inside the black hole now. We can't see it, but it's still there, just inaccessible. Fine. But wait, black holes evaporate. Stephen Hawking figured this out in 1974, 19 years after Einstein died. Black holes emit radiation due to quantum effects near the event horizon. They lose mass, they shrink, and eventually, after an unimaginably long time, they disappear completely. So now what happens to the information? The book is gone, the black hole is gone, the information was never radiated back out. Hawking radiation is just thermal radiation, random heat. It doesn't encode the specific information about what fell in. So where did the information go? Did it just vanish? That's a problem, a big problem. In quantum mechanics, information is never destroyed. This is fundamental, it's called unitarity. The quantum state of a system evolves in a way that preserves information. You can scramble it, encrypt it, spread it out. but you can't delete it. If you burn that book, the information isn't destroyed. It's in the smoke, the ash, the heat radiation, the atoms scattered into the air. In principle, if you knew the exact quantum state of all those particles, you could reconstruct what the book said. It's absurdly impractical, but it's theoretically possible. Information is preserved. But a black hole, if it evaporates and the information is just gone, that breaks quantum mechanics. It breaks one of the deepest principles we have. Einstein never had to think about this. Not because he wasn't smart enough, not because he wasn't interested in black holes, though he wasn't really, but because the framework to even ask this question didn't exist during his lifetime. Quantum mechanics in Einstein's era was still being developed. The Copenhagen interpretation, the uncertainty principle, Schrödinger's equation, yes, those existed. Einstein knew them. He argued with Bohr about them. He hated them. God does not play dice with the universe. You've heard that quote. Einstein's rejection of the probabilistic nature of quantum mechanics. He thought quantum mechanics was incomplete, that there were hidden variables underneath, that the randomness was just ignorance, not fundamental. He never accepted quantum mechanics fully. He spent the last decades of his life trying to find a unified field theory that would replace quantum mechanics with something deterministic, something that made sense to him. He failed. But more than that, he never had the tools to think about black holes quantum mechanically. Quantum field theory, the framework that treats particles as excitations of fields, was still being developed. Feynman, Schwinger, Tominaga, they worked out quantum electrodynamics in the late 1940s and early 1950s. Feynman won the Nobel Prize for it in 1965, a decade after Einstein's death. Hawking radiation, 1974. The information paradox became clear in the 1970s and 1980s. Einstein missed all of it. He never had to answer the question, what happens to information in a black hole? And here's the thing, this isn't a side issue, this isn't a technical detail. This is the question that breaks the universe. If information is destroyed in black holes, quantum mechanics is wrong. One of the most successful theories in the history of physics, verified to absurd precision in countless experiments, is fundamentally broken. Or general relativity is wrong. The event horizon isn't really a one-way membrane. Something happens there that we don't understand. Something that lets information escape. Or both are wrong. And we need a new theory, quantum gravity, that replaces both in extreme conditions. This is where Feynman comes in, because Feynman didn't share Einstein's discomfort with quantum mechanics. He built it, he invented half of it, and Feynman didn't avoid black holes because they were uncomfortable. He asked what quantum mechanics actually predicts at the event horizon. He asked what happens to information. Einstein never asked that question. He couldn't. The framework didn't exist. But Feynman could. And what he found was stranger than Einstein ever imagined. Feynman's quantum approach to gravity, 1960s. Caltech. Richard Feynman is at the height of his powers. He's already won the Nobel Prize. Well, he will in 1965, but the work is done. Quantum electrodynamics, QED, the theory of how light and matter interact, the most precisely tested theory in all of physics. Predictions accurate to 10 decimal places. 10. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. Feynman invented half of it, the path integral formulation. Feynman diagrams, the techniques everyone uses to calculate quantum processes. But he's not done. He never is. He starts thinking about gravity. Now, gravity is Einstein's domain. general relativity, space-time curvature, elegant, geometric, beautiful, but it's not quantum, and Feynman knows that's a problem, because everything else is quantum. Electromagnetism, quantum. The strong nuclear force, quantum. The weak nuclear force, quantum. Gravity, classical. It doesn't make sense. At some level, gravity has to be quantum too. So Feynman asks, can we treat gravity like we treat electromagnetism? In QED, light is carried by photons, particles of light. The electromagnetic force is mediated by photon exchange. An electron emits a photon, another electron absorbs it, and they feel a force. That's how forces work quantum mechanically. What if gravity works the same way? What if there are gravitons, particles that carry the gravitational force? You have mass, I have mass. We attract each other gravitationally. In Einstein's picture, that's because we both curve space-time and follow geodesics in that curved space. In Feynman's picture, you emit gravitons. I absorb them. We exchange gravitons back and forth, and that exchange creates the force we call gravity. It's a completely different way of thinking about it. Einstein, gravity is geometry. Feynman, gravity is particle exchange. Now you might think these are incompatible. You might think you have to choose one or the other. But here's the beautiful thing. At low energies in weak gravitational fields, they give the same answer. Feynman can calculate the force between two masses using graviton exchange, and he gets Newton's law of gravitation. The same law Einstein's theory reduces to in weak fields. The math works. But Feynman pushes further. He develops path integral methods for quantum gravity, the same techniques he used for QED. You sum over all possible paths a particle can take, all possible histories, and the sum gives you the probability of what actually happens. For gravity, you sum over all possible space-time geometries. Let that sink in. Not all possible paths through space-time. All possible space-times. Every possible way space and time could be shaped. Every possible curvature, every possible topology. You sum over all of them, weighted by their action, and out comes the quantum behavior of gravity. It's ambitious, it's audacious, it's beautiful, and it doesn't work. Well, it works at low energies. It works for weak gravitational fields. But when you try to push it to high energies, near black holes, at singularities, at the Big Bang, the math explodes. You get infinities. Not the controlled infinities that you can remove with renormalization, like in QED. Uncontrollable infinities. The theory breaks down. Feynman knows this. He's honest about it. In his lectures, he says outright, quantum gravity is hard, maybe too hard, maybe we're missing something fundamental. But here's what matters. Feynman doesn't give up. He doesn't say, gravity is geometry, leave it at that. He asks, what do quantum mechanics and general relativity predict together near a black hole? Einstein never asked that question. He couldn't. He didn't trust quantum mechanics, but Feynman does. And when you apply quantum mechanics near an event horizon, when you take seriously the idea that particles are quantum fields, that vacuum isn't empty but seething with virtual particles, when you combine that with the extreme space-time curvature of a black hole, strange things happen. Hawking would figure this out a decade later. The event horizon creates particles, real particles from virtual fluctuations. The black hole radiates. But Feynman was already thinking in that direction. He was already asking, what does quantum field theory predict near a horizon? He introduces gravitons into his thinking about black holes, not as a complete theory, not as a solution, but as a tool. a way to think about what's happening. In Einstein's picture, a black hole is a passive object. Mass curves space-time. That's it. In Feynman's picture, a black hole is active. It's exchanging gravitons. It's interacting with quantum fields. It's not isolated from the quantum vacuum around it. This changes everything. Because if a black hole is quantum, if it's interacting with fields, then it's not truly black. It radiates. It evolves. It's a dynamical quantum object, not a static geometric solution. Einstein's black holes are eternal, unchanging. Feynman's black holes live and die. This is the shift. This is what Feynman understood that Einstein missed. Gravity isn't just geometry. It's quantum. And when you take that seriously, black holes stop being the end of physics. They become the beginning of a deeper question. What happens to information at the event horizon when quantum mechanics matters? Feynman didn't solve this. Nobody has, not completely. But he asked it, he framed it, he gave us the tools to think about it. Einstein never got there. He was too committed to geometry, too skeptical of quantum mechanics, too uncomfortable with the implications. Feynman had no such hang-ups. He looked at a black hole and saw a quantum field theory problem, and that made all the difference. The Wheeler-Feynman collaboration context. You want to understand why Feynman thought about black holes the way he did? You have to understand John Wheeler, John Archibald Wheeler, the man who coined the term black hole, the man who became obsessed with gravitational collapse, with singularities, with the breakdown of physics at the edge of space-time. And he was Feynman's mentor, Princeton, 1939. Feynman arrives as a graduate student. He's 21, brilliant, cocky, irreverent. He's already developed his own methods, his own ways of thinking about physics. He doesn't fit in. He doesn't want to. Wheeler's 28, young for a professor. He's working on nuclear physics fission, the cutting edge of the time. They start working together, and it's one of the most productive collaborations in the history of physics. Wheeler asks big questions, crazy questions, questions that sound impossible. What if there's no such thing as a particle? What if electrons are just knots in the electromagnetic field? What if we could reformulate electromagnetism so that there's no field at all, just direct action at a distance between charges? Most physicists would dismiss these questions. Too speculative, too weird. Feynman loves them. He and Wheeler developed the Wheeler-Feynman absorber theory, a reformulation of electromagnetism where charges interact directly with each other, forward and backward in time. It's bizarre, it works. It doesn't replace standard electromagnetism, but it shows you can think about the same physics in radically different ways. This is what Wheeler does. He makes you question your assumptions. He makes you ask what's really fundamental and what's just the way we've chosen to describe things. And then World War II happens. Feynman goes to Los Alamos, works on the atomic bomb. Wheeler works on reactors, on plutonium production. They're separated, but after the war, they stay in touch. Wheeler moves to different problems, and in the 1950s, he becomes fascinated with general relativity. This is unusual. Most physicists in the 1950s don't care about general relativity. It's a solved problem. Einstein figured it out. It's beautiful, sure, but it's not relevant to particle physics, nuclear physics, the stuff people are working on. Wheeler doesn't care. He starts thinking about gravitational collapse. What happens when a star runs out of fuel and collapses under its own gravity? Chandrasekhar had figured out in the 1930s that there's a limit. If a white dwarf star is too massive, more than about 1.4 solar masses, Electron degeneracy pressure can't hold it up. It has to collapse further. It becomes a neutron star. Neutrons packed so tightly that a teaspoon of the stuff weighs 1 billion tons. But what if it's even more massive? What if neutron degeneracy pressure isn't enough? Then it collapses all the way. Nothing stops it. It forms a singularity, a black hole. Wheeler becomes obsessed with this. He starts running seminars at Princeton on gravitational collapse. He invites the best relativists in the world. He pushes them to think about the unthinkable. What happens at the singularity? What happens at the event horizon? Can you really have a place in the universe where time stops, where physics breaks down? Einstein hated these questions. He avoided them. Wheeler runs toward them. And he's in contact with Feynman the whole time. They're not collaborating directly on black holes. Feynman is at Caltech working on particle physics, QED, path integrals. Wheeler is at Princeton thinking about stars and collapse in space-time. But they talk, they write letters, they visit each other. Wheeler tells Feynman about his ideas, about gravitational collapse, about the paradoxes at the event horizon. And Wheeler asks his signature provocative questions. What happens to quantum mechanics near a singularity? If space-time curvature becomes infinite, does quantum field theory break down? Can information escape from inside an event horizon? These aren't idle questions. Wheeler is serious. He wants answers. Feynman doesn't have answers, not complete ones. But the questions stick, because Feynman realizes something. General relativity and quantum mechanics have barely been combined. People treat them as separate. You use general relativity for cosmology, for stars, for large-scale structure. You use quantum mechanics for atoms, particles, fields. But near a black hole, you need both, and nobody's really done that carefully. Wheeler knows this. He's been thinking about it for years. But Wheeler is a relativist. He thinks in terms of geometry, space-time, curvature. Feynman is a quantum field theorist. He thinks in terms of particles, fields, path integrals. They're approaching the same problem from different directions. And when Wheeler coins the term black hole in 1967, it's not just a name, it's a provocation. He's saying, this isn't a frozen star. This isn't a collapsed object. This is something new, something we don't understand. A hole in space-time, a place where our theories fail. And Feynman hears that. He's already been thinking about quantum gravity on and off for years. But Wheeler's obsession with black holes gives him a concrete problem to focus on. Not quantum gravity in general. Quantum gravity ain't near an event horizon. What does quantum mechanics predict there? Feynman starts lecturing on this at Caltech in the early 1960s. He's working through it in real time, in front of students trying to figure out what happens when you take quantum field theory seriously in curved space-time. He doesn't solve it, he's honest about that, but he lays out the problem more clearly than anyone has before. And here's the key. Wheeler gave him permission to ask the question. Einstein wouldn't have. Einstein would have said, black holes probably don't form in nature, don't worry about it. But Wheeler said, black holes are real, they're important, and we didn't understand them, figure it out. That's the context. That's why Feynman approached black holes the way he did. Not because he was smarter than Einstein, but because he had a mentor who asked different questions. Einstein avoided black holes. Wheeler embraced them. And Feynman, learning from Wheeler, didn't just embrace them. He tried to break them open with quantum mechanics. That's what Einstein missed. Not the math, not the physics. The willingness to ask the uncomfortable question. Feynman's lectures on gravitation, 1962-63, 1962, Caltech. Feynman decides to teach a course on gravitation. This is unusual. Feynman is known for particle physics, for QED, for quantum mechanics. He's not a relativist. He's not an expert on general relativity, but he wants to understand it, really understand it from the ground up. So he does what Feynman always does when he wants to understand something. He teaches it. The course runs from 1962 to 1963. It's small. Graduate students, postdocs, maybe a dozen people. Feynman starts with the basics: equivalence principle, geodesics, how mass curves space-time. But he doesn't teach it the way Einstein taught it. He doesn't teach it the way relativists teach it. He teaches it like a quantum field theorist trying to make sense of a geometric theory. He derives Einstein's equations not from pure geometry, but from the properties gravitons would have to have if gravity were a field theory. He asks, if I assume gravity is mediated by a massless spin-2 particle, what equations does that particle have to obey? And he gets Einstein's field equations. Different route, same destination, but the route matters. Because it shows you can think about general relativity as a field theory, not just as geometry, and that opens up new questions. Then he gets to black holes. He doesn't call them that. Wheeler hasn't coined the term yet. He calls them collapsed objects or Schwarzschild solutions. But he's thinking about them hard. He works through the Schwarzschild metric, the math of a spherically symmetric, non-rotating black hole. He shows the students what happens at the event horizon, how time appears to stop for a distant observer, how nothing can escape from inside, standard stuff. This is in every general relativity textbook, but then he does something different. He asks, what does quantum mechanics predict near the event horizon? This is 1962. Hawking won't discover Hawking radiation until 1974. Nobody's really thought carefully about quantum fields in curved spacetime, but Feynman starts thinking about it. He considers a quantum field, say the electromagnetic field, near the event horizon. In flat space-time, in ordinary empty space, the vacuum isn't really empty. It's full of virtual particles. Particle-antiparticle pairs popping in and out of existence, borrowing energy from the uncertainty principle, then annihilating before anyone notices. This isn't speculation. This is real. We measure it. The Casimir effect, the Lamb shift, these are experimental confirmations that the vacuum is full of quantum fluctuations. Now, what happens to these fluctuations near an event horizon? Feynman realizes something. The event horizon isn't a physical barrier. It's not a wall. It's just a mathematical surface where something dramatic happens to the geometry. But if you're a particle, you don't care about that surface. You're just following the laws of quantum mechanics. So virtual particles are still popping in and out of existence near the horizon. But here's the thing, space-time is curved there, dramatically curved. And in curved space-time, the notion of particle becomes ambiguous. What looks like vacuum to one observer might look like particles to another observer, especially if one observer is accelerating or in a strong gravitational field. This is called the Unruh effect, though it won't be fully understood until the 1970s. But Feynman is already thinking in this direction. He's asking, if I'm near an event horizon, do I see particles that a distant observer doesn't see? He doesn't solve this. He doesn't derive Hawking radiation. That takes more sophisticated techniques, developed later. But he sees the problem. He sees that quantum mechanics and black holes don't fit together cleanly. He sees that you can't just take Einstein's classical solution and call it done. Quantum mechanics changes things. Now, the lectures were never meant to be published. They were informal. Feynman was working through ideas in real time. He made mistakes, corrected them, speculated, backtracked. But Fernando Morinigo and William Wagner, two graduate students, took detailed notes. And years later, decades later, those notes were edited and published as Feynman Lectures on Gravitation. They came out in 1995. Feynman had died in 1988. He never saw them in print. But they reveal something important. Feynman was thinking about quantum effects near black holes in the early 1960s, before Wheeler coined the term, before Penrose proved singularity theorems, before Hawking discovered radiation. He didn't solve the problem. He didn't discover what Hawking discovered, but he framed the question. He showed that black holes aren't just a general relativity problem. They're a quantum mechanics problem. And when you treat them that way, when you take quantum fields seriously near the horizon, you start to see cracks in the classical picture. Feynman knew the classical picture was incomplete. Einstein thought it was wrong and tried to argue black holes didn't exist. Feynman thought it was right, but insufficient. Black holes exist, but there's more to the story, and he was right. Hawking would prove it 12 years later. But Feynman saw it coming. He saw that the event horizon isn't the end. It's where quantum mechanics and gravity collide. And when they collide, something has to give. Information has to go somewhere. Energy has to escape. The black hole has to evaporate. Feynman didn't derive the equations, but he understood the principle. Einstein never understood the principle. He died before the framework existed, but Feynman lived through the quantum revolution. He helped build it, and when he turned that quantum toolkit toward black holes, he saw things Einstein couldn't see. Not because Einstein wasn't brilliant, but because Einstein was working with half the tools. Feynman had the other half, and that made all the difference. Point 6. Particle production near event horizons. Let's talk about nothing. Empty space, vacuum. You think it's empty? It's not. In quantum mechanics, vacuum is seething, churning, full of activity you can't see. Virtual particles. Particle-antiparticle pairs popping into existence, existing for a tiny fraction of a second, then annihilating. Electron-positron pairs. Quark-antiquark pairs, photons splitting into particle pairs and recombining. They're called virtual because they violate energy conservation. They borrow energy from the vacuum, from the uncertainty principle. Heisenberg says you can violate energy conservation as long as you do it fast enough that nobody can measure it. They tend to borrow a lot of energy, you have to pay it back quickly. The particles exist for maybe 10-23 seconds, then they're gone. This isn't philosophy, this is real, we measure it. The Casimir effect, put two metal plates very close together in a vacuum. The vacuum between them has fewer virtual particles than the vacuum outside because only certain wavelengths fit between the plates. The pressure difference pushes the plates together, measurable force. From nothing, the Lamb shift, virtual particles around an electron change its energy levels slightly. We measure this in hydrogen atoms to incredible precision. Virtual particles are real. The vacuum is not empty. Now, put that vacuum near a black hole. Feynman starts thinking about this in the early 1960s. He's teaching his gravitation course. He's working through quantum field theory in curved space-time. And he asks, what happens to virtual particles near an event horizon? Here's the setup. You're hovering just above the event horizon of a black hole, not crossing it. Just floating there, fighting the gravity with your rocket engines. The vacuum around you is still doing its thing, virtual particle pairs still popping into existence. But now there's something new. Tidal forces. Tidal forces. The difference in gravitational pull between your head and your feet. Near a black hole, these forces are extreme. Astronomers call it spaghettification. You get stretched. Now think about a virtual particle pair, an electron and a positron, say. They pop into existence very close to each other. Normally, they'd annihilate almost immediately. But near the event horizon, the tidal force pulls them apart. One particle gets pulled toward the black hole, the other gets pushed away. And if this happens right at the event horizon, something remarkable occurs. One particle falls across the horizon. It's gone. It can't come back. The other particle escapes to infinity. They can't annihilate anymore. They're separated by the event horizon, by a one-way barrier in space-time. So both particles become real. The one that escaped is a real particle now. It has positive energy. It can be detected. The one that fell in, from the perspective of energy accounting, it has negative energy. It reduces the mass of the black hole. This is particle creation from vacuum, from nothing. The black hole's gravitational field rips virtual particles apart and makes them real. Feynman saw this coming. He didn't have the full calculation. That would take more sophisticated techniques, tools that weren't quite ready yet in the early 1960s. But he understood the principle. Quantum field theory in curved space-time doesn't just sit there. It does things. It creates particles. And near a black hole, where space-time curvature is extreme, this creation process becomes significant. Stephen Hawking formalized this in 1974. He did the full calculation. He used quantum field theory in the curved space-time of a Schwarzschild black hole. He carefully tracked how particle creation works near the horizon, and he found that black holes radiate. They emit particles, real particles, with a thermal spectrum like a hot object. The temperature is tiny. For a solar mass black hole, it's about 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background. But it's not zero. Black holes aren't black. They glow. They emit Hawking radiation. And because they're emitting energy, they're losing mass. MC2. Mass and energy are the same thing. The black hole shrinks. Eventually, over an incomprehensibly long time, 1067 years for a solar mass black hole, it evaporates completely. Gone. This shocked everyone. Before Hawking's calculation, black holes were thought to be eternal. Once formed, they'd exist forever, just sitting there, swallowing anything that got too close. But quantum mechanics changes that. Black holes live and die, and Feynman saw it coming. Not the exact mechanism, not the precise calculation, but the idea. He knew that quantum fields near an event horizon would do something strange. He knew that the vacuum wouldn't just be vacuum. He knew that particle creation had to happen. Einstein never thought about this. How could he? His framework is classical, deterministic, no virtual particles, no quantum fluctuations, no uncertainty principle. In Einstein's general relativity, a black hole is a solution to the field equations. It's geometry. Space-time curvature, that's it. Nothing comes out, nothing escapes. The event horizon is a perfect one-way membrane, but that's only true classically. Quantum mechanically, the picture changes. The event horizon becomes a place where quantum processes occur, where particles are created, where the black hole interacts with the quantum vacuum. It's not passive, it's active. Feynman understood this because he understood quantum field theory. He built half of it. He knew what quantum fields do. He knew they fluctuate. He knew they create particles. And when you put those fluctuating fields into the curved space-time of a black hole, they don't stop fluctuating. They do something dramatic. They turn virtual particles into real ones. They make the black hole radiate. Now there's a deeper point here. Hawking radiation isn't just about black holes glowing. It's about the connection between gravity, thermodynamics, and quantum mechanics. When Hawking calculated the radiation spectrum, he found it was thermal. Perfect blackbody radiation, a specific temperature. T bar 3 over 8 PGR MKB. That's the Hawking temperature. It depends on the black hole's mass. But temperature implies entropy, thermodynamics. Jacob Bekenstein had already suggested in 1973 that black holes have entropy, that they obey the laws of thermodynamics. The entropy is proportional to the area of the event horizon. S*** KBC3A, 4G area, not volume. This is bizarre. For normal objects, entropy is proportional to volume. More stuff, more disorder, more entropy. But for black holes, it's the surface area that matters. This is a hint, a deep hint. It suggests that the information about what's inside a black hole is somehow encoded on its surface. On the event horizon, holography, the idea that a volume of space can be described by information on its boundary. This has become one of the deepest ideas in modern theoretical physics. And it all starts with Hawking radiation, which starts with Feynman's insight. Quantum fields do things near event horizons. Einstein never got here. He couldn't. He didn't trust quantum mechanics. He thought it was incomplete. He spent decades trying to replace it with something deterministic. He never accepted that God plays dice. But God does play dice. And near a black hole, those dice create particles. Feynman accepted this. He embraced it. He asked what happens when you take quantum mechanics seriously in the most extreme gravitational field possible. And the answer is, black holes aren't black. They glow, they evaporate, they die. Einstein's black holes were eternal tombs. Feynman's black holes, or Hawking's, but Feynman saw it coming, are temporary, dynamic, quantum. This is what Einstein missed, not because he wasn't smart, but because he was working in the wrong framework. Classical physics can't see Hawking radiation. It's fundamentally quantum. You need virtual particles. You need the uncertainty principle. You need quantum field theory. Feynman had all of that. Einstein had none of it. Or rather, he had it but rejected it. And that's why he missed what black holes really are. Not endpoints, not singularities where physics stops, but quantum objects where physics becomes stranger and more beautiful than we ever imagined. Point 7. The renormalization problem in curved space-time. Feynman had a gift for making the impossible possible. Quantum electrodynamics, QED, was a disaster in the 1930s and 1940s. The theory gave infinite answers to simple questions. What's the mass of an electron? Infinity. What's its charge? Infinity. How much does it interact with light? Infinity. The math was broken. People thought the whole theory was wrong. Feynman, along with Schwinger and Tominaga, fixed it. Renormalization. The trick is this: the infinities come from virtual particles at very high energies, very short distances. You can't measure physics at infinitely short distances, so you don't. You absorb the infinities into the definitions of measurable quantities, the electron's measured mass, measured charge. You redefine the theory in terms of what you can actually observe. and the infinities disappear, or rather they hide. They're still there in the math, but they don't affect predictions. QED becomes the most successful theory in physics. Predictions accurate to 10 decimal places. Feynman wins the Nobel Prize for this in 1965. But here's the thing. Renormalization works for QED. It works for the weak force. It works for the strong force. Eventually, with quantum chromodynamics, it doesn't work for gravity. Feynman knew this. He tried. In his 1962-63 lectures on gravitation, he explored whether you could treat gravity as a quantum field theory and renormalize it the same way. You can't. The infinities don't go away. They multiply. They cascade. You remove one infinity, 2 more appear. You remove those, 4 more appear. It's uncontrollable. The technical reason, gravity is non-renormalizable. It's a fundamental property of the theory. General relativity, quantized naively, produces infinities you can't absorb into a finite number of measurable parameters. You'd need infinitely many measurements to make infinitely many predictions. The theory loses predictive power. This doesn't mean gravity isn't quantum, it means our approach is wrong. We're missing something. Now, for most situations, this doesn't matter. Quantum gravity effects are tiny. They become important only at the Planck scale. Distances of about 1035 meters, energies of about 1019 GeV. Far, far beyond anything we can probe experimentally. For atoms, molecules, even nuclei, you can ignore quantum gravity. General relativity is classical. Quantum mechanics is flat space-time. They're separate. Everything works. But near a black hole, near a singularity, you can't ignore it anymore. Feynman realized this. He understood that black holes are places where quantum gravity matters, where you can't separate the quantum and the gravitational, and he understood that we don't have the tools to calculate what happens there. Let me be specific. At the event horizon of a solar mass black hole, space-time curvature is strong, but not Planck scale strong. You can still use semi-classical methods, quantum fields on a classical curved background. That's what Hawking did to derive Hawking radiation. But at the singularity, the Schwarzschild singularity at r⁻0, curvature becomes infinite, density becomes infinite. Classical general relativity says the laws of physics break down, and quantum field theory doesn't save you. It makes things worse. Because quantum field theory in curved space-time has infinities. And near a singularity where curvature is infinite, those infinities become uncontrollable. Feynman saw this clearly. He said in his lectures, "We do not know the correct laws of physics at very short distances or very high energies. We suspect that quantum mechanics and general relativity combined break down." This is radical honesty. Einstein never said this. Einstein thought general relativity might be wrong in its predictions. He doubted black holes formed, but he didn't think the theory itself broke down. Feynman is saying our theories fail, both of them. Quantum mechanics and general relativity, our 2 greatest achievements in physics, are incomplete. They're incompatible at extremes, and black holes force you to confront that. Because a black hole singularity is a place where quantum mechanics matters. Because things are small, dense, energetic, and where gravity matters. Because curvature is infinite. You need both theories. And they don't fit together. This is the renormalization problem in curved space-time. It's not just a technical issue. It's a signal that we're missing something fundamental. String theory tries to fix this. It replaces point particle with extended strings, smoothing out the short distance behavior, making the infinities controllable. Loop quantum gravity tries to fix this. It quantizes space-time itself, making it discrete at small scales, cutting off the infinities. Other approaches exist. None are proven. None have experimental confirmation. But they all agree on one thing. You need a quantum theory of gravity, and black holes are where that theory is necessary. Feynman didn't develop such a theory. He worked on quantum gravity, explored it, but never found a complete solution. But he understood the problem better than almost anyone. He understood that the breakdown isn't a failure of physics. It's a guide. It's telling you where to look for new physics. Einstein never understood this. Einstein thought black hole singularities were unphysical, that nature would prevent them, that his equations were predicting something impossible, so the prediction must be wrong. Feynman thought differently. He thought, if the equations predict a breakdown, maybe that breakdown is real. Maybe it's telling us that new physics kicks in there. Physics we haven't discovered yet. The singularity isn't a flaw in the theory, it's a boundary, a place where the theory reaches its limit and hands off to something deeper. What is that something? We don't know, not yet. But Feynman saw that the question is worth asking. He saw that black holes aren't just interesting astrophysical objects. They're laboratories for extreme physics. Places where our current theories fail and new theories must emerge. Einstein avoided the singularity. Feynman ran toward it. And here's the deepest point. The renormalization problem in curved spacetime isn't just about calculations. It's about information. When you can't control the infinities, you lose predictive power. You can't calculate what happens. And if you can't calculate what happens, you can't track information. This connects to the information paradox. If physics breaks down at the singularity, if our equations give nonsense answers, then we can't say what happens to information that falls into a black hole. Does it get destroyed? Does it escape? Does it get encoded somehow in the Hawking radiation? We don't know. The renormalization problem is a technical version of the information problem. Both are saying we don't have the right theory yet. Feynman understood this in the 1960s. Einstein never did. He died a decade earlier, thinking black holes probably didn't exist, but they do exist. And they're telling us something. They're telling us that quantum mechanics and general relativity are not the final word. They're telling us there's deeper physics waiting to be discovered. Feynman knew how to listen to that message. Einstein never heard it. Not because he wasn't brilliant, but because he was asking different questions. Einstein asked, can black holes form? Feynman asked, what happens if they do? And that question, what actually happens, leads you straight to the edge of known physics, to the place where our best theories break down, to the place where new discoveries are waiting. That's what Einstein missed. Not the math, not the geometry, but the opportunity. The opportunity to see that black holes aren't the end of physics. They're the beginning of the next revolution. There it is. Point 8, time dilation and quantum uncertainty. Time is not absolute. You know this. Einstein figured it out in 1905. Special relativity. Time passes at different rates for observers moving at different speeds. Then 1915, general relativity. Time also passes at different rates in different gravitational fields. The stronger the gravity, the slower time passes. This is real, this is measured. GPS satellites have to correct for this. They're in a weaker gravitational field than we are on the surface. Time passes faster for them, about 45 microseconds per day faster. If you don't correct for this, GPS would be wrong by several miles within a day. Time dilation is not a curiosity, it's engineering. But near a black hole, time dilation becomes extreme. Let's make this concrete. You're watching your friend descend toward a black hole. She's falling in, crossing the event horizon. From your perspective, far away from the black hole, watching with a telescope, what do you see? You see her slow down. The closer she gets to the event horizon, the slower she moves. Her clock ticks slower. The light from her gets redshifted, stretched to longer and longer wavelengths. At the event horizon, from your perspective, time stops. She never crosses. She's frozen there, forever. Of course, from her perspective, she crosses just fine. Nothing special happens at the horizon. She falls through in finite time. But you never see that. To you, she's stuck at the horizon, approaching it asymptotically, never quite reaching it. This is classical time dilation, Einstein's general relativity. Well understood. But Feynman asked a different question. What does quantum mechanics do when time slows down like this? Heisenberg's uncertainty principle. You know it. V dt, two energy and time are conjugate variables. The more precisely you know one, the less precisely you know the other. If you measure energy over a very short time interval dt, there's a large uncertainty in energy dE. This is why virtual particles can exist. They borrow energy dE from the vacuum, but they only exist for time dot, as long as their product is small enough. Heisenberg allows it. Now, what happens when time stretches? Near the event horizon, from an outside observer's perspective, time slows down. A clock that ticks once per second far away might tick once per year near the horizon. Or once per millennium, time intervals dt become enormous. And if d is enormous, then d can be tiny. Energy uncertainty shrinks. Quantum fluctuations that happen over long time intervals have very precise energies. This means something strange. The quantum vacuum near an event horizon, from the perspective of a distant observer, looks different from the quantum vacuum far away. The fluctuations are stretched, amplified, changed. Feynman saw this. He realized that time dilation doesn't just affect clocks and observers. It affects quantum fields. The vacuum itself is time-dependent near a black hole. The notion of particle becomes observer-dependent. What looks like vacuum to someone falling through the horizon looks like a bath of particles to someone hovering far away. This is the Unruh effect, though it wouldn't be fully formalized until the 1970s by William Unruh. If you accelerate through vacuum, flat, empty space-time, you see particles. A thermal bath of particles. The temperature depends on your acceleration. T, A, 2 pCAK-B, where A is your acceleration. Accelerate hard enough. You see a hot bath of particles. Even though someone not accelerating sees nothing. Near a black hole, if you hover just above the event horizon, you have to accelerate to resist falling in. That acceleration makes you see particles. But there's more. The time dilation itself creates structure at the horizon. Think about a quantum fluctuation. An electron-positron pair popping into existence. Normally they exist for maybe 10-21 seconds. Then they annihilate. But near the horizon, time is stretched. From a distant observer's perspective, that fluctuation lasts much longer. Long enough to interact with other fields. Long enough to affect measurable quantities. The quantum foam of the vacuum, normally too fast, too fleeting to notice, becomes slow, stretched, observable near a black hole. Feynman understood that this creates a rich structure. The event horizon isn't just a geometric surface. It's a place where quantum mechanics and time dilation conspire to create observable effects. Hawking radiation emerges from this. The particle creation process I described earlier, virtual particles ripped apart by tidal forces, is intimately connected to time dilation. The distant observer sees particle creation because their time coordinate is different from the time coordinate of someone falling in. There's no single correct definition of what counts as a particle near the horizon. It's observer dependent. This is deeply weird. In flat space-time, everyone agrees on what a particle is. An electron is an electron. A photon is a photon. But in curved space-time, especially near an event horizon, that agreement breaks down. One observer's vacuum is another observer's particle bath. Einstein never thought about this. He couldn't. He had time dilation. He understood that time passes differently in different gravitational fields, but he didn't have quantum field theory. He didn't have the uncertainty principle applied to fields. He didn't have the framework to ask, what happens to quantum fluctuations when time stretches? Feynman had that framework. He combined time dilation with quantum uncertainty and saw that something has to happen at the horizon. The quantum vacuum can't just sit there passively. It responds to the space-time curvature, to the time dilation. It produces particles. Now there's an even deeper connection. Quantum uncertainty in energy and time means that measuring anything near the event horizon becomes problematic. If you try to measure the energy of a particle very close to the horizon, where time is dilated enormously, the uncertainty in energy becomes large. You can't tell precisely what the energy is. And if you can't measure energy precisely, you can't track information precisely. This feeds into the information paradox. If quantum uncertainty is amplified by time dilation, and if that uncertainty prevents you from tracking what happens to particles near the horizon, then how can you be sure information is preserved? Maybe it's not destroyed, maybe it's just smeared, uncertain, hidden behind a combination of time dilation and quantum fuzziness. Feynman didn't solve this. Nobody has solved this completely, but he saw the connection. He saw that time dilation and quantum uncertainty aren't separate effects. They interact, and near a black hole, that interaction creates something new. Something Einstein's purely classical treatment missed entirely. Einstein had time dilation. He described it perfectly. But without quantum mechanics, he couldn't see what time dilation does to quantum fields. Feynman could, and what he saw was that the event horizon is alive with quantum activity. Virtual particles stretched by time dilation, energy uncertainty amplified, observer-dependent particle creation. The horizon isn't a simple boundary, it's a quantum interface, a place where the deterministic, geometric beauty of general relativity collides with the probabilistic, fluctuating nature of quantum mechanics. And from that collision, something emerges. Hawking radiation, information scrambling, observer-dependent reality. Einstein never saw any of this. He saw the horizon as a mathematical surface where light cones tip over, where time stops. Feynman saw it as a place where quantum mechanics does something extraordinary, where time dilation and uncertainty combine to create particles from nothing, where the vacuum becomes tangible, where physics becomes strange in a way Einstein never imagined. That's what Einstein missed, not the geometry, but the quantum reality living on top of that geometry. 3.9. The interior solution mystery. What's inside a black hole? You cross the event horizon, you're inside. What do you see? Einstein's equations give an answer.
You keep falling. Space-time keeps curving. You fall toward the singularity. And at r equals 0, at the center, you hit the singularity, infinite curvature, infinite tidal forces. You're crushed to 0 volume. You cease to exist as anything recognizable. The math says so. The Schwarzschild solution, Einstein's field equations, they all point to the same conclusion. At the singularity, physics stops. But does it?
Feynman asked a different question. He asked, are these interior solutions physically meaningful? Just because the math gives you an answer doesn't mean that answer describes reality. Math can do lots of things. You can write down equations that produce infinities. But infinities aren't physical. If your theory predicts infinity, that's not a prediction, that's a breakdown. Feynman understood this from quantum field theory. In QED, if you calculate naively, you get infinite answers. The electron's self-energy is infinite, but you don't take that literally. You recognize it as a signal that you're probing distances where the theory breaks down. You renormalize. Maybe the same thing happens at the singularity. Maybe the singularity isn't real. Maybe it's just a signal that general relativity has reached its limit. But then what happens instead? Feynman explored whether quantum mechanics might step in. Here's the idea. As you fall toward the singularity, density increases, curvature increases. Classical physics says it goes to infinity, but quantum mechanics resists compression. The uncertainty principle. If you squeeze a particle into a smaller and smaller region of space, its momentum uncertainty increases. The XDP child to squeeze it into 0 volume, momentum uncertainty goes to infinity. The particle has infinite kinetic energy. That energy creates pressure, quantum pressure. It resists further compression. This is degeneracy pressure. It's what holds up white dwarf stars, electron degeneracy pressure. It's what holds up neutron stars, neutron degeneracy pressure. But both have limits. Above a certain mass, degeneracy pressure fails. The star collapses. Classically, it collapses all the way to a singularity. But quantum mechanically? Feynman wondered, maybe there's another source of pressure. Maybe quantum field effects, quantum geometry, something we don't understand yet, kicks in at Planck scale densities and stops the collapse. Maybe the singularity never forms. Maybe the interior of a black hole isn't infinite density at a point. Maybe it's finite density at the Planck scale, held up by quantum pressure. This is speculative. Feynman knew it was speculative, but it's a reasonable speculation because we know general relativity breaks down at Planck scales. We know quantum gravity must be important there. And if quantum gravity prevents infinite density, then the singularity is an artifact of using classical general relativity where it doesn't apply. The real interior might be something completely different. Maybe it's a Planck star, a tiny region of extremely high but finite density, held up by quantum effects. Maybe it's a wormhole, space-time tunneling through to another region or another universe. Maybe it's something we don't have words for yet. The point is, we don't know. The interior of a black hole is hidden behind the event horizon. We can't see it, we can't measure it, and our theories break down there. So any prediction about what's inside is tentative. Einstein took the singularity seriously. He thought it was a problem with the theory, evidence that black holes don't form in nature. Feynman took it differently. He thought maybe the singularity is telling us we need new physics there. Not that black holes don't exist, but that their interiors are described by quantum gravity, not classical general relativity. This is a fundamentally different attitude. Einstein, If the theory predicts something absurd, avoid the situation. Feynman, if the theory predicts something absurd, that's where new physics hides. Now there's another mystery about the interior. Once you cross the event horizon, you can't escape. That's the definition of the event horizon. But what about information? You fall in. You carry information with you. The specific quantum state of every particle in your body, every atom, every bit, that information crosses the horizon. Classically, it's gone, lost to the outside universe forever. But quantum mechanically, information must be preserved. Unitarity, the quantum state evolves deterministically. Information can be scrambled, spread out, hidden, but not destroyed. So what happens to it? Hawking radiation is thermal, random. It doesn't encode specific information about what fell in. If the black hole evaporates completely and the radiation's thermal, the information is gone. That's the information paradox. Feynman was aware of this problem, though it wasn't fully formulated until the 1970s and 1980s, and he suspected the resolution had something to do with the interior. Maybe information doesn't fall to the singularity. Maybe it's encoded at the horizon. Maybe it escapes in subtle correlations in the Hawking radiation. Maybe the interior solution, the mathematical description of what's inside, is misleading. Maybe the horizon is more fundamental than the interior. This idea has gained traction. The holographic principle, developed in the 1990s by T. Hooft and Susskind, suggests that everything inside a black hole, all the information, all the physics, is encoded on the event horizon. The interior might be an illusion, a redundant description. The real physics happens at the boundary. Feynman didn't articulate this fully, but he was thinking in that direction. He was asking, what is the interior really? Is it a place, or is it a mathematical construction that doesn't correspond to physical reality? Einstein never asked this. For Einstein, the interior was a region of space-time, just like the exterior. You could write down the metrics, solve the equations, describe geodesics. But Feynman, with his quantum perspective, saw that the interior might be fundamentally inaccessible. And if it's inaccessible, maybe it's not physical. Maybe physics only cares about what can be measured, and the interior can't be measured from outside. So maybe the question, what's inside a black hole, doesn't have a physical answer. Maybe it's like asking, what happened before the Big Bang? A question that assumes a framework that doesn't apply. This is radical, but it's in line with quantum mechanics. Quantum mechanics only predicts measurable outcomes. It doesn't describe unobservable realities. If the interior is unobservable, maybe quantum mechanics doesn't describe it. Maybe it doesn't exist in the way we think it does. Feynman played with these ideas. He didn't commit to them. He was too careful for that. But he raised the questions, and those questions have driven decades of research. People are still trying to figure out what's inside a black hole, whether the singularity is real, whether information is preserved, whether the interior is physical or mathematical. We don't have answers yet. But we're asking the right questions, and Feynman is the one who taught us to ask them. Einstein gave us the equations that predict black holes, but Feynman asked whether those predictions describe reality, or just the limits of the equations. That's the difference. Einstein trusted the math, Feynman questioned it, and in physics, questioning is how you discover what's actually true. Point 10, Hawking radiation as Feynman's legacy, 1974, Cambridge University. Stephen Hawking is 32 years old. He's already made major contributions to general relativity. Singularity theorems with Roger Penrose, the area theorem for black holes. He's also been diagnosed with ALS for over a decade. He's in a wheelchair, he can barely speak, but his mind is sharper than ever, and he's about to discover something that will change physics forever. Hawking is thinking about quantum fields near black holes. He's using the tools Feynman helped develop: quantum field theory, path integrals, particle creation in curved space-time. He's doing the calculation carefully. Quantum fields on the curved space-time background of a Schwarzschild black hole, and he finds something shocking. Black holes emit radiation, thermal radiation, a perfect black-body spectrum. The temperature depends on the black hole's mass. Smaller black holes are hotter. TMR C3 8 PGM kb. For a solar mass black hole, that's about 60 nanokelvin. Tiny, far colder than the cosmic microwave background. But for a small black hole, a primordial black hole, maybe the mass of a mountain, the temperature could be millions of degrees, hot enough to glow in gamma rays. Hawking presents this at a conference. People don't believe him. John Wheeler is there. He challenges Hawking. Black holes don't radiate. That's the definition of a black hole. But Hawking has done the calculation. He's checked it multiple times. Black holes radiate. It takes a few months for the community to accept it. Other physicists repeat the calculation. They get the same answer. Hawking is right, and physics is never the same. Because Hawking radiation means black holes aren't eternal. They evaporate. Slowly, over astronomical timescales, but they evaporate. A solar mass black hole would take 1067 years to evaporate, far longer than the current age of the universe. But a small black hole formed in the early universe might evaporate in the lifetime of the universe, or already have evaporated. Black holes die. This is Hawking's discovery, Hawking's calculation, Hawking's name on it, but it's Feynman's legacy, because everything Hawking used came from Feynman. Quantum field theory and curved space-time, Feynman explored it in his 1962-63 lectures. Particle creation from vacuum, Feynman discussed it. Path integral methods, Feynman invented them. The conceptual framework that black holes are quantum objects, not just classical geometric solutions. Feynman established it. Hawking did the detailed calculation. He deserves full credit for that. But the groundwork was Feynman's. Feynman saw that black holes and quantum mechanics had to interact. He didn't derive Hawking radiation, but he set the stage. He asked the questions. He developed the tools. He showed that you should think about black holes quantum mechanically. And Hawking followed through. Now, Hawking radiation has profound implications. First, thermodynamics. If black holes have temperature, they have entropy. Einstein had already argued this in 1973. The entropy is proportional to the event horizon's area. Schwarzschild KKBC3A 4G, the Bekenstein-Hawking entropy. This is one of the most important formulas in theoretical physics. It connects gravity, quantum mechanics, and thermodynamics. Three pillars of physics unified in one equation. And it's weird, for normal objects, entropy is proportional to volume. More stuff, more microstates, more entropy. But for black holes, it's the surface area. Why? Nobody knew at first. It's still debated, but it suggests that information about the black hole's interior is somehow encoded on the surface, on the event horizon. Holography. The idea that a three-dimensional volume of space can be fully described by information on its two-dimensional boundary. This has become central to modern theoretical physics. String theory. ADS-CFT correspondence. It all traces back to Bekenstein-Hawking entropy. and that traces back to Hawking radiation. And that traces back to Feynman's insight that black holes are quantum. Second implication, the information paradox. If black holes evaporate and the radiation is thermal, random, with no information about what fell in, then information is destroyed. That breaks quantum mechanics. This is the paradox I mentioned earlier. It's still not fully resolved. People have proposed solutions. Maybe the radiation isn't perfectly thermal. Maybe subtle correlations encode the information. Maybe the information escapes at the very end, when the black hole is small and quantum effects dominate. Maybe the interior of the black hole is connected to the radiation through some kind of quantum entanglement. Firewalls, ER, EPR, exotic ideas, none are proven. The debate continues. But here's the point. This is one of the deepest problems in theoretical physics, and it exists because of Hawking radiation, which exists because Feynman showed us how to think about black holes quantum mechanically. Third implication, black holes are thermodynamic systems. They have temperature, entropy, energy. They obey the laws of thermodynamics. First law, energy conservation. If you throw mass into a black hole, its mass increases. If it radiates, its mass decreases. Second law, entropy increases. The area of the event horizon can never decrease, classically. Hawking radiation complicates this, but the generalized second law, including the entropy of the radiation, still holds. Third law, you can't reach absolute zero temperature. You can't make a black hole with zero surface gravity. Black holes aren't just exotic objects. They're the most efficient engines in the universe for converting mass to energy. They're thermodynamic laboratories. Einstein never saw black holes this way. He saw them as geometric solutions, static, eternal, no dynamics, no thermodynamics. Feynman saw them as physical objects that could do things, that could interact with quantum fields, emit particles, evolve over time, and Hawking proved Feynman right. Now, Feynman and Hawking never collaborated directly on black holes, but they influenced each other. Feynman's lectures on gravitation, published posthumously in 1995, show he was thinking about quantum effects near horizons in the early 1960s. Hawking was a student in the 1960s, learning general relativity and quantum field theory. He was absorbing Feynman's methods, Feynman's approach. When Hawking calculated black hole radiation, he used Feynman's tools, path integrals, quantum field theory, the idea that you can calculate particle creation by summing over all possible field configurations. This is Feynman's methodology applied to Einstein's black holes, and it revealed something Einstein never knew. Black holes are not black. They glow, they hiss, they evaporate. They are quantum objects embedded in a quantum universe. This is Feynman's legacy. Not that he discovered Hawking radiation, he didn't. Hawking did, but that he made it possible to discover. He built the framework. He asked the questions. He showed that quantum mechanics and black holes must be combined. Einstein built the theory that predicts black holes. Feynman built the theory that explains them. And Hawking used Feynman's theory to discover what black holes actually do. That's how science works. One person lays the foundation, another builds the structure, another discovers what the structure can do. Einstein, Feynman, Hawking. Each generation sees further by standing on the shoulders of the previous one. But here's what matters for this video. Einstein missed Hawking radiation not because he died too early, though he did. He missed it because he was working in the wrong framework. He had general relativity but not quantum field theory. He had geometry but not particles. He had determinism, but not uncertainty. Feynman had all of those. And because he had them, he could almost see, that black holes radiate. He didn't do the final calculation, but he saw the path to it. And that's what Einstein missed. Not the math, not the intelligence, but the willingness to combine quantum mechanics with gravity and see what emerges. Hawking radiation emerged, and with it, a new understanding of black holes, not as cosmic tombs where physics ends, but as quantum furnaces where physics becomes richer, stranger, more beautiful than we ever imagined. That's Feynman's gift to us. The understanding that black holes aren't the end, they're a doorway to new physics, to deeper truths, to questions we're still trying to answer. Einstein gave us the door, but Feynman showed us how to open it. The information paradox seeds. Here's a question that seems simple. You burn a book. Where does the information go? The words, the letters, the specific arrangement of ink on paper, where does it go? Into the smoke, the ash, the heat, the scattered carbon atoms, the photons radiating away. It's scrambled, spread out, mixed up with everything else. But in principle, if you knew the exact quantum state of every particle of smoke, every atom of ash, every photon, you could reconstruct the book. You could work backward through the combustion chemistry, trace every molecule, unscramble the information. It's impossible in practice. The information is scattered across billions of particles, hopelessly mixed with thermal noise. But it's possible in principle. This is unitarity, a fundamental principle of quantum mechanics. Information is never destroyed. The quantum state of a system evolves deterministically according to the Schrödinger equation. You can scramble information, encrypt it, spread it across the universe, but you cannot delete it. This has been tested exhaustively. Every quantum experiment confirms it. Information is conserved. Now, throw that book into a black hole. What happens to the information? The book falls past the event horizon. It's gone. You can't see it anymore. You can't interact with it. Eventually, maybe in milliseconds, maybe in hours, depending on the black hole's size, the book hits the singularity. It's crushed, destroyed. The information was in the book. Now the book is gone. Where's the information? You might say it's inside the black hole. Still there, just inaccessible. Fine, but black holes evaporate. Hawking radiation. The black hole slowly loses mass, shrinks, eventually disappears completely. And the radiation, it's thermal, random, like the heat from a fire. It doesn't encode what fell in. It doesn't carry information about the book. A black hole that swallowed Shakespeare looks the same as a black hole that swallowed a phone book. Same mass, same radiation spectrum. The radiation is determined entirely by the black hole's mass, charge, and spin, nothing else. So when the black hole evaporates completely, poof, gone. Where did the information go? It's not in the radiation. The radiation is thermal. It's not inside the black hole. The black hole doesn't exist anymore. So it's destroyed. That breaks quantum mechanics. This is the black hole information paradox. And Feynman saw it coming, not in full detail. The paradox wasn't fully formulated until the 1980s and 1990s, after Hawking's 1974 discovery of black hole radiation. But Feynman understood the tension. In his lectures in the early 1960s, before Hawking radiation was even discovered, Feynman was already asking, what happens to quantum information in strong gravitational fields? He understood that general relativity and quantum mechanics make contradictory predictions. General relativity says information that falls past the event horizon is causally disconnected from the outside. It's gone. The exterior universe can never get it back. Quantum mechanics says information is always preserved. It can't be destroyed. One of these has to be wrong, or both are wrong, or our understanding of what happens at the event horizon is wrong. Feynman didn't resolve this. How could he? The full paradox requires Hawking radiation, which wasn't discovered until after Feynman's main work on black holes. But he planted the seeds. He showed that you have to take quantum mechanics seriously near black holes. You can't just use classical general relativity. And when you do take quantum mechanics seriously, contradictions appear. Let me be specific about why this is such a deep problem. In 1976, Hawking himself argued that information is destroyed in black holes. He said the radiation is exactly thermal, no correlations, no hidden information. What falls in is lost forever. This means quantum mechanics is wrong, or at least incomplete. Pure states, quantum states with definite information, evolve into mixed states, thermal states with no information. Unitarity is violated. Hawking was serious about this. He thought black holes represent a fundamental breakdown of quantum mechanics. Most physicists disagreed violently. Leonard Susskind, Gerard de 't Hooft, and others argued that information must be preserved. They didn't know how, but they were certain it was. The debate raged for decades. Hawking finally conceded in 2004. He admitted that information is probably preserved, though the mechanism was still unclear. But even today in 2026, we don't have a complete resolution. We have ideas, proposals, partial solutions. Maybe the radiation isn't exactly thermal. Maybe there are subtle correlations that encode information. You'd need to measure huge numbers of particles, track their quantum states precisely, but in principle, the information is there. Maybe information escapes gradually throughout the evaporation process, encoded in quantum entanglement between the radiation and the shrinking black hole. Maybe information escapes at the very end, when the black hole becomes Planck-sized and quantum gravity effects dominate. Maybe the interior and exterior of the black hole are quantum mechanically connected in a way we don't understand. Firewalls, wormholes, ER, the idea that entanglement and space-time geometry are the same thing. Exotic ideas, speculative ideas, none proven. But here's what we know for sure. There's a paradox, a real, deep, unresolved paradox. And it exists because black holes sit at the intersection of quantum mechanics and general relativity. Einstein never encountered this paradox. He died in 1955. Hawking radiation wasn't discovered until 1974. The information paradox wasn't clearly formulated until the 1980s. He never had to confront the question, what happens to information in a black hole? But even if he'd lived longer, he wouldn't have engaged with it the way Feynman did, because Einstein didn't trust quantum mechanics. He thought it was incomplete. He spent the last decades of his life trying to replace it with a deterministic theory. The EPR paper in 1935, Einstein, Podolsky, Rosen arguing that quantum mechanics can't be a complete description of reality. God does not play dice. Einstein wanted hidden variables, deterministic evolution, local realism. He never accepted the Copenhagen interpretation. He never accepted that quantum mechanics is fundamentally probabilistic. So how could he engage with a paradox that assumes quantum mechanics is correct? He couldn't. He didn't want to. Feynman had no such hang-ups. Feynman built quantum mechanics. He understood it deeply, intuitively. He knew it was right. QED predictions accurate to 10 decimal places. You don't argue with that. So when quantum mechanics and general relativity make contradictory predictions about black holes, Feynman didn't doubt quantum mechanics. He doubted that we understood general relativity correctly in extreme conditions. Or he doubted that classical general relativity was the full story. Or he suspected there's new physics, quantum gravity, that resolves the contradiction. But he never doubted that information is conserved. That's the difference. Einstein would have questioned quantum mechanics. Feynman questioned everything else. And that's why Feynman could see the paradox forming. Even before Hawking radiation made it explicit, he saw that black holes force you to choose quantum mechanics or general relativity. You can't have both. Not as they're currently formulated. Something has to give. Now, why does this matter? Because the information paradox isn't just about black holes. It's about the nature of reality. If information can be destroyed, then the universe isn't deterministic at the quantum level. The future isn't determined by the past, even in principle. That's radical. That changes everything we think we know about physics. If information is preserved, then black holes are far stranger than we thought. The event horizon isn't a simple one-way membrane. Something happens there, something we don't understand, that allows information to escape. Either way, we're missing something fundamental. Feynman understood this. He understood that black holes aren't just astrophysical curiosities. They're laboratories for testing our deepest theories. They're places where our theories make contradictory predictions, and contradictions are where new physics hides. Einstein avoided the contradictions. He argued black holes don't form, so we don't have to worry about them. Feynman embraced the contradictions. He said if our theories contradict each other, that's telling us something important. That's the hallmark of great physics, not avoiding the hard questions, running toward them. Einstein ran away from black holes. Feynman ran toward them. And the paradox Feynman helped uncover, the information paradox, is still driving research today. Quantum information theory, holography, AD-SCFT, black hole thermodynamics, quantum error correction. Entire fields of physics are trying to solve this problem. Because if we can figure out what happens to information in a black hole, we'll understand something deep about how the universe works. We'll understand the relationship between quantum mechanics and gravity. We'll understand space-time at the deepest level. Feynman didn't solve it, he seeded it. He planted the question, what happens to quantum information near an event horizon? And physicists have been trying to answer ever since. That's Feynman's legacy here, not the answer, the question. Einstein never asked it, and that's what he missed. Gravitons and the quantum structure of space-time. Einstein thought space-time was smooth, a fabric, a continuum. You can zoom in as far as you want, infinitely far, and it's still smooth, still continuous, like a rubber sheet. Stretch it, curve it, bend it. Mass curves space-time. Objects follow geodesics in that curved space. That's gravity. Beautiful, elegant, geometric. But Feynman suspected it was wrong. Not wrong in the usual regime. General relativity works brilliantly for planets, stars, galaxies. The predictions match observations to incredible precision. But at the smallest scales, at the Planck scale, Feynman thought space-time might not be smooth. It might be granular, discrete, quantized, made of tiny, indivisible units. Let me back up. Everything else in physics is quantized. Energy, quantized. Photons carry discrete chunks of energy. E, Audieck-Schwarz angular momentum, quantized. Electrons in atoms have specific, discrete angular momentum values. Electric charge, quantized. Comes in multiples of the electron charge, E. Even fields are quantized. The electromagnetic field is made of photons. Particle-antiparticle pairs pop in and out of the vacuum. Everything is discrete at the quantum level. Why should space-time be different? Feynman asked this question in the 1950s and 60s. If everything else is quantum, space-time should be too. But how do you quantize space-time? In Einstein's theory, gravity isn't a force in the usual sense. There's no gravitational field pulling on things. There's just curved geometry. Mass curves space-time. Objects move along straight lines, geodesics, in that curved space. No force, just geometry. But Feynman thought, what if we treat gravity like the other forces? Electromagnetism is mediated by photons. The electromagnetic force happens because charged particles exchange photons. The strong nuclear force is mediated by gluons. Quarks exchange gluons. The weak nuclear force is mediated by W and Z bosons. That's how beta decay works. What if gravity is mediated by particles too? Gravitons. Hypothetical particles that carry the gravitational force. You have mass, I have mass, we attract each other gravitationally. In Einstein's picture, we both curve space-time and follow geodesics. In Feynman's picture, we exchange gravitons. You emit gravitons, I absorb them. That exchange creates the force. Different picture. But at low energies, same predictions. Feynman worked this out. You can derive Newton's law of gravitation from graviton exchange. You can even derive corrections that match general relativity in weak fields. The math works, but gravitons have specific properties. They're massless, like photons. They're spin-2 particles, not spin-1 like photons or gluons. Spin-2, this is important. The spin determines how the particle couples to matter, how it creates forces. Spin-2 means gravitons couple to energy and momentum. Everything with energy, which is everything, couples to gravity. That's why gravity is universal. It affects everything. Now, if gravitons exist, then space-time is quantum, because gravitons are quantized. They come in discrete units. And if the gravitational field is made of gravitons, then the field itself is granular, not smooth. Zoom in far enough to the Planck length, about 1035 meters, and you'd see the granularity. Space-time wouldn't be a smooth fabric. It would be foamy, fluctuating, bubbling with quantum uncertainty. Virtual gravitons popping in and out of existence. Space-time geometry fluctuating, quantum foam. John Wheeler coined that term, quantum foam. The idea that at the Planck scale, space-time is wildly fluctuating, with virtual black holes and wormholes constantly forming and dissolving. Feynman explored this. He calculated what quantum fluctuations of the gravitational field would look like, and he found they're enormous at short distances. In QED, virtual photons create small corrections. The electron's mass gets shifted slightly. Its magnetic moment gets corrected. But these are small effects, controlled by the fine structure constant, A1137. In quantum gravity, the effects aren't small. The coupling strength of gravity increases with energy. At the Planck energy, about 1019 GeV, quantum gravitational effects become as strong as the interactions themselves. Space-time itself becomes uncertain. You can't talk about a definite position or a definite time at distances smaller than the Planck length or time shorter than the Planck time. Space-time breaks down as a meaningful concept. This is radical. Einstein's smooth space-time, gone. At the Planck scale, there might not be a space-time in the usual sense. There might be something else. A quantum structure we don't understand yet. Feynman understood this. He understood that if you take quantum mechanics seriously and apply it to gravity, space-time can't be fundamental. It must emerge from something deeper, maybe from gravitons, maybe from something else. But the smooth, continuous space-time of general relativity is an approximation, valid at large scales, breaking down at small scales. Now, near a black hole singularity, you reach those small scales. Classical general relativity says space-time curvature becomes infinite at r0, but if space-time is quantized, there's no such thing as infinite curvature. There's a maximum curvature, a smallest length scale, the Planck length. You can't compress space-time smaller than that. It doesn't make sense. The concept breaks down, so the singularity might not exist, not as a point of infinite density, but as a region where space-time becomes quantum, where geometry dissolves into quantum foam, where our classical concepts fail. Feynman didn't prove this. Nobody has. But he saw the direction. He saw that quantum gravity must modify the black hole interior, must prevent the classical singularity, must replace it with something, we don't know what. Loop quantum gravity proposes that space-time is made of discrete loops, a spin network. The singularity is replaced by a quantum bounce, space-time compressed to the Planck scale, then bouncing back. String theory proposes that fundamental objects are strings, not points. Strings smooth out singularities. The infinite curvature is replaced by intense but finite string interactions. Other approaches exist, none proven, but they all agree. At the Planck scale, space-time is not smooth. Einstein never imagined this. For Einstein, space-time is fundamental. It's the stage on which physics happens. You can curve it, warp it, but it's always there, always continuous. The idea that space-time itself might be emergent, might be built from something more fundamental, never occurred to him. How could it? The Planck scale was barely understood in his time. Quantum field theory didn't exist in mature form, but Feynman had the tools to think about it. He had quantum field theory, he had path integrals, he had the conceptual framework to ask, what happens when you quantize space-time? And he found it becomes discrete, granular, foamy. At least that's the suspicion. The calculations are hard. Quantum gravity is unsolved, but the principle is clear. If gravity is quantum, space-time is quantum. And if space-time is quantum, it can't be smooth all the way down. There's a smallest scale, a fundamental graininess. Black holes force you to confront this, because at the singularity, you reach the Planck scale. Classical smooth space-time fails. Quantum space-time, whatever that is, takes over. Einstein saw the singularity as a problem, a breakdown of his theory. Feynman saw it as a clue, a sign that space-time is quantum. That's the difference in perspective. Einstein, space-time is fundamental, and the singularity shows general relativity needs modification or doesn't apply there. Feynman, space-time is emergent, and the singularity shows where it emerges from something deeper. We're still trying to figure out what that something deeper is. Gravitons, spin networks, strings, something else entirely. We don't know. But Feynman pointed the way. He showed that you can't understand black holes without understanding the quantum structure of space-time. Einstein never got there. He thought in terms of smooth geometry. Feynman thought in terms of quantum particles. And when you think in terms of particles, gravitons, you realize space-time itself must be made of something. That's what Einstein missed. Not because he wasn't brilliant, but because the conceptual framework didn't exist in his time. Quantum field theory, the success of renormalization, the understanding that fields are made of particles, all of that came after Einstein's main work. Feynman had it, and he used it to see further, to see that space-time, like everything else, is quantum, and that changes everything. The membrane paradigm connection. Here's a practical problem. You want to calculate what happens when matter falls into a black hole. You could try to solve Einstein's field equations for the full dynamical space-time. Matter falling in, black hole growing, space-time evolving. Good luck. Einstein's equations are nonlinear partial differential equations. They're brutal. Even for static symmetric situations, they're hard. For dynamical asymmetric situations, essentially impossible without massive computer simulations. And even if you could solve them, you'd face the singularity. The place where the equations break down, where curvature becomes infinite, where physics stops. What do you do there? Most physicists in Einstein's time avoided the problem. Too hard, too messy, too uncomfortable. But in the 1970s and 80s, a group of physicists at Caltech and MIT developed a different approach. They asked, what if we don't try to solve for the interior? What if we treat the event horizon as a physical surface, a membrane with its own properties? A membrane that you can interact with that has temperature, viscosity, electrical conductivity. A membrane that you can do calculations on without worrying about the singularity inside. This is the membrane paradigm. And it works beautifully. Kip Thorne, Richard Price, Douglas MacDonald, they formalized this in the 1980s. But the conceptual seeds came from earlier, from Wheeler's ideas about black holes as physical objects, from Baconstein's work on black hole thermodynamics, and from Feynman's insistence that you should be able to calculate observable quantities without solving the impossible parts. Let me explain how it works. The event horizon isn't a physical surface. There's nothing there. An infalling observer crosses it without noticing anything special. But from the perspective of an outside observer, someone far from the black hole, the horizon looks like a surface. Time slows down there. Light gets infinitely redshifted. Nothing ever quite crosses from the outside view. So treat it like a surface. Give it properties. Temperature? Yes, the Hawking temperature. T or C3, 8 PGM KB. Entropy? Yes, the Bekenstein-Hawking entropy. S for A, KB, BC3A, 4G. Viscosity? Yes, the horizon resists shear. If you try to make it rotate non-uniformly, it fights back. Electrical conductivity? Yes. If you dump electric charge onto a black hole, the charge spreads out over the horizon. The surface behaves like a conductor with a specific resistivity. Surface gravity? Yes. The acceleration you'd need to hover just above the horizon. All of these are well-defined, calculable quantities. And here's the magic. You can use these properties to calculate what happens when you interact with a black hole. Drop matter in, the horizon's area increases, its temperature changes slightly. You can calculate all of this without ever solving for the interior. Spin up the black hole, the horizon develops viscosity effects. Energy gets dissipated. You can calculate the back reaction. Apply an electromagnetic field, the horizon responds with induced currents. You can solve for the fields outside without worrying about inside. The membrane paradigm turns black holes into tractable problems. You don't solve Einstein's equations in the interior. You don't worry about the singularity. You just treat the horizon as a membrane with known properties and calculate. This is a Feynman-style approach. Feynman was famous for finding shortcuts. Clever ways to calculate things without solving the full, impossible problem. Feynman diagrams. Instead of solving quantum field equations exactly, you draw diagrams representing particle interactions and calculate probabilities directly. Path integrals. Instead of solving the Schrödinger equation, you sum over all possible paths and get the quantum amplitude. Feynman didn't invent the membrane paradigm, but the spirit of it, finding an effective description that lets you calculate observable quantities, that's pure Feynman. And it relies on understanding that the horizon has quantum properties. Temperature, entropy, these are quantum concepts. Classically, in Einstein's general relativity, the event horizon is just a geometric surface. It has no temperature, no entropy, no physical properties. But quantum mechanically it does. Hawking radiation gives it temperature. Bekenstein's arguments give it entropy. And once you have temperature and entropy, you have thermodynamics. You can treat the horizon as a thermodynamic system. That's what the membrane paradigm does. It takes the quantum properties of the horizon, discovered through Feynman-style thinking, and uses them to build an effective classical description. You don't need to solve quantum gravity. You don't need to know what happens at the singularity. You just need to know how the horizon behaves as a boundary. And you can calculate that. This has been incredibly useful. Astrophysicists use the membrane paradigm to model accretion black holes, matter spiraling in from a disk, X-ray emissions, jet formation. Gravitational wave physicists use it to understand black hole mergers. Two horizons colliding, merging, settling down. Theoretical physicists use it to study black hole thermodynamics, to explore the information paradox, to test ideas about quantum gravity. It's a practical tool, and it exists because people realize the horizon is more than geometry. It has quantum structure. Einstein's purely geometric approach didn't anticipate this. For Einstein, the horizon is defined by the condition G0, 0 in the Schwarzschild coordinates. A coordinate singularity, not a physical one. There's nothing special there physically. It's just a place where certain coordinates break down. You can choose different coordinates, Kruskal coordinates, Eddington-Finkelstein coordinates, and the horizon isn't even a special surface anymore. So why would you treat it as a physical membrane? From Einstein's perspective, you wouldn't. But from Feynman's perspective, from the quantum perspective, the horizon is special. It's where particle creation happens. It's where information might be encoded. It's where quantum and gravitational effects combine. It's a boundary between the observable universe and the interior. And boundaries are important in quantum mechanics. In quantum field theory, boundaries have physical significance. They affect vacuum states, energy spectra, particle creation. The Casimir effect happens because metal plates create boundaries that change the vacuum energy. The Unruh effect happens because accelerated observers have event horizons, boundaries in space-time that change what they see as particles. Black hole horizons are the ultimate boundaries, and treating them as membranes with physical properties is the natural quantum approach. Einstein couldn't do this. He didn't have the quantum framework. Feynman did. And the membrane paradigm, developed decades after Feynman's main work on black holes, embodies his approach. Don't solve the impossible problem. Find the effective description, calculate the observables, trust quantum mechanics to give the horizon physical properties. Use those properties to make predictions. It's pragmatic, it's effective, it's deeply Feynman. And it's something Einstein never imagined, because Einstein was trying to solve the complete problem, the full geometry, the exact solution. Feynman was trying to calculate what you can actually measure, different goals, different methods, different insights. The membrane paradigm shows that you don't need to understand the interior to understand the physics. You just need to understand the boundary, and that's a quantum insight. One that Einstein, for all his geometric brilliance, never had. Black holes as quantum information processors, Leonard Susskind calls black holes the ultimate quantum computers. Not computers in the sense of devices we build, computers in the sense of physical systems that process information according to quantum rules. And black holes might be the most efficient information processors in the universe. This is a completely modern view, 1990s and 2000s. Quantum information theory applied to black holes, but it traces back to Feynman. Let me explain. Information is physical. This seems obvious now, but it was controversial. In the early days of computer science, people thought of information as abstract. Bits, logical operations, mathematics. It doesn't matter what physical system implements the bits. Vacuum tubes, transistors, optical switches, the information is the same. But in the 1960s and 70s, people realized information has physical costs. Rolf Landauer showed that erasing information generates heat. There's a minimum energy cost to erase one bit, K bar B equal ln2. This isn't an engineering limitation. It's fundamental thermodynamics. Information is physical. It takes energy to manipulate. It takes space to store. Feynman explored this in the 1980s. He asked, can you build a computer that operates on quantum principles? A quantum computer. Classical bits are 0 or 1. Quantum bits, qubits, can be superpositions. 0 and 1 at the same time. This allows quantum computers to process information differently, to explore multiple computational paths simultaneously. Feynman showed this could be powerful. Certain problems that are impossible for classical computers might be tractable for quantum computers. Simulating quantum systems, for instance. Factoring large numbers, searching databases. Quantum computers are now being built. Google, IBM, startups. They work. They're limited, but they work. But the most extreme quantum computer might be a black hole. Here's why. A black hole has entropy, the Bekenstein-Hawking entropy. S B C3A, 4G, where A is the area of the event horizon. Entropy measures information, specifically the number of microstates, the number of different ways the system could be arranged internally while looking the same externally. S KB on O, where O is the number of microstates. For a black hole, the entropy is huge. A solar mass black hole has an event horizon area of about 1014 square meters. Plug that into the formula. The entropy is about 1077 QB. That corresponds to 1077 bits of information. That's staggering. More information than in all the matter that fell in to form the black hole if you just counted the particles. Where is this information? It must be encoded somehow on the event horizon. 1 bit per Planck area. That's the maximum information density the universe allows. The event horizon is covered in bits, quantum bits, qubits, and when matter falls in, information gets encoded on the horizon. The black hole processes this information, scrambles it, mixes it with all the other information already there. Eventually, the information comes back out in the Hawking radiation. This is the picture that's emerged over the last few decades. Black holes don't destroy information, they scramble it, maximally. They're the ultimate information scramblers. You throw in a book, the information gets encoded on the horizon, it gets mixed with everything else. Eventually, after the black hole evaporates, the information is in the radiation, but it's scrambled beyond recognition. You'd need to capture every single photon of Hawking radiation, measure its quantum state perfectly, and perform an impossibly complex quantum computation to extract the original information. Impossible in practice, but possible in principle. Information is preserved. This view, black holes as quantum information processors, comes from taking Feynman's insights seriously. Quantum mechanics is about information, quantum states, entanglement measurement. If black holes are quantum objects, they process information quantum mechanically. Susskind, Nettehoeft, Maldacena, Polchinski, modern theorists building on this. They study black hole information scrambling. How fast does information get mixed? There's a limit. The fastest possible scrambling time is proportional to Qr/kBt, where T is the temperature. Black holes saturate this limit. They scramble information as fast as quantum mechanics allows. They're maximally chaotic quantum systems. This has profound implications. If black holes are quantum computers, we can apply quantum information theory to them. Entanglement entropy, quantum error correction, complexity theory. These are tools from computer science and quantum mechanics, and they're now central to understanding black holes. For instance, the firewall paradox. If you try to track information carefully, you find that the event horizon should be covered in high-energy particles, a firewall. An infalling observer would burn up, contradicting the equivalence principle. This paradox arises from thinking carefully about quantum entanglement at the horizon. It's unresolved. But the fact that we can even formulate it comes from treating black holes as quantum information systems. Einstein never thought this way. For Einstein, black holes, if they existed, were geometric objects. Curved space-time singularities, geodesics, not information, not qubits, not quantum computers. Feynman didn't develop the full quantum information view either. He died in 1988 before much of this was worked out, but he set the stage. He showed that quantum mechanics applies to gravity, that black holes are quantum, that you need to think about quantum states, not just classical fields. And once you think that way, information becomes central, because quantum mechanics is ultimately about information. The Schrödinger equation evolves quantum information. Measurement extracts information. Entanglement distributes information. Apply that to black holes, and you get the modern view. Black holes as the universe's most extreme information processors, encoding information on their horizons, scrambling it maximally, returning it in Hawking radiation. This is light years beyond Einstein's geometric picture. And it's only possible because Feynman taught us to think about black holes quantum mechanically. Einstein gave us the geometry, Feynman gave us the quantum framework, and modern physicists combine them to see black holes as information processors. That's the progression, and it shows how far we've come. From Einstein's reluctance to even accept black holes exist, to Feynman's quantum approach, to the modern view, black holes are quantum systems that process information according to the laws of quantum mechanics. The universe's ultimate computers, encoding reality on a two-dimensional surface, processing quantum information at the maximum possible rate. That's what Einstein missed. Not because the idea existed in his time, it didn't, but because he never took the quantum step. He never asked, if black holes are quantum, what does that mean? Feynman asked, and the answer is still unfolding. The holographic principal origins. Here's one of the strangest ideas in modern physics. Everything happening in a three-dimensional volume of space, every particle, every field, every interaction, can be completely described by information on the two-dimensional boundary of that volume. The 3D world is a hologram, a projection from a 2D surface. This is the holographic principle, and it started with black holes. With Bekenstein and Hawking's discovery that black hole entropy is proportional to area, not volume. Let me walk you through this. Normally, entropy is extensive. It's proportional to volume. Take a box of gas. Double the volume, you double the entropy. Makes sense. More space, more molecules, more ways to arrange them. This is true for everything we're familiar with. Stars, planets, oceans, atmospheres. Entropy scales with volume, but not for black holes. Black hole entropy is proportional to the area of the event horizon. S Yamarar KB 3AR 4G, not the volume inside, the area of the surface. This is weird. It suggests that all the information about what's inside the black hole, every particle that fell in, every quantum state, is somehow encoded on the two-dimensional event horizon, not in the three-dimensional interior, on the surface. Jacob Bekenstein noticed this in the early 1970s. He was a graduate student of John Wheeler. Wheeler asked him, what happens to entropy when you throw it into a black hole? Second law of thermodynamics says total entropy can never decrease. But if you throw entropy into a black hole, it disappears behind the horizon. Gone. Lost to the external universe. Doesn't that violate the second law? Bekenstein said, not if the black hole itself has entropy. If the black hole's entropy increases when you throw stuff in, the total entropy, matter plus black hole, still increases. He calculated what the black hole's entropy should be, and he found it's proportional to area. This was before Hawking radiation, before anyone knew black holes have temperature. Hawking's discovery in 1974 confirmed it. Black holes have temperature, and temperature times entropy gives energy relations that match thermodynamics perfectly. But the area dependence remained mysterious. Why area? Why not volume? Gerard 't Hooft thought about this in the 1990s. He realized if entropy is information and black hole entropy is proportional to area, then information is fundamentally two-dimensional. Everything inside a black hole is encoded on its surface. Then Leonard Susskind extended this. He said, this isn't just about black holes. It's about space-time itself. Any region of space has a maximum entropy, and that maximum is proportional to the surface area of the region, not its volume. The holographic bound. The maximum information content of a region is A for LP, where A is the surface area and LP is the Planck length. 1 bit per Planck area. This means the three-dimensional universe we experience is, in some sense, a hologram. All the information is encoded on a two-dimensional surface. The 3D reality is a projection, a reconstruction from that 2D data. This sounds like philosophy, like science fiction, but it's been made precise. The AD-CFT correspondence, discovered by Juan Maldacena in 1997, is a concrete realization. It shows that a theory of quantum gravity in a certain type of space-time, anti-de Sitter space, is exactly equivalent to a quantum field theory on the boundary of that space-time. The gravity theory lives in the bulk, 3 spatial dimensions plus time. The field theory lives on the boundary, 2 spatial dimensions plus time. They're the same theory, different descriptions of the same physics. The 3D gravitational reality is holographically encoded in the 2D boundary theory. This has been tested mathematically. Calculations in the gravity theory match calculations in the boundary theory. It's not speculation. It's a proven duality in certain cases, and it all traces back to black hole entropy. To the observation that information in a black hole is encoded on the horizon's area. Feynman didn't discover the holographic principle. That came later, to Hooft and Susskind in the 1990s, but Feynman's work set the foundation. He showed that you have to think about black holes quantum mechanically. He showed that quantum information matters. He explored how quantum fields behave near horizons. All of that was necessary for the holographic principle to emerge, because the holographic principle is fundamentally about quantum information in gravitational systems. You can't derive it from classical general relativity alone. You can't derive it from quantum field theory in flat space-time alone. You need both. You need quantum gravity, and black holes are where quantum gravity matters. Einstein had classical general relativity, no quantum mechanics. He could never have conceived of the holographic principle. For Einstein, space-time is three-dimensional plus time. Real, geometric, fundamental. The idea that the third dimension is somehow redundant, that all the physics happens on a 2D surface, would have been incomprehensible. Feynman had quantum mechanics. He had information theory. He had the conceptual tools. He didn't put them together into holography, but he enabled those who did. And now, holography is central to theoretical physics. It's changed how we think about space-time. Maybe space-time isn't fundamental. Maybe it emerges from quantum entanglement patterns on a boundary. Maybe the universe is fundamentally lower dimensional than we experience. Maybe space itself is holographic. These are the questions people are asking now. And they all started with a simple observation. Black hole entropy scales with area, not volume. An observation that only makes sense if you think quantum mechanically. An observation Einstein never made. Feynman didn't make it either. Bekenstein and Hawking did. But Feynman created the framework that made it possible. He showed that black holes are quantum objects. And once you think that way, once you take quantum mechanics seriously near horizons, holography becomes almost inevitable, because information can't disappear. And if it can't disappear into the interior, it must be on the surface. And if it's on the surface for black holes, maybe it's on surfaces everywhere. Maybe the universe itself is a hologram. That's how far we've come. From Einstein's reluctance to even accept black holes, to Feynman's quantum approach, to the modern view that space-time might be emergent from quantum information on boundaries. It's a revolution in how we think about reality. And it started with black holes, with taking them seriously as quantum objects. That's what Einstein missed. The quantum nature of gravity, the information content of space-time, the possibility that dimensions are holographic. All of it invisible to classical general relativity. All of it obvious, or at least accessible, once you think quantum mechanically. Feynman thought quantum mechanically. Einstein didn't, and that made all the difference. Firewall, Paradox and Modern Debates, 2012. A paper drops that shakes theoretical physics. 4 authors, Ahmed Almheri, Donald Marolf, Joseph Polchinski, James Sully. They call it the AMPS paper after their initials, and it claims something shocking. If you fall into a black hole, you don't gently cross the event horizon like Einstein said. You burn up. There's a firewall, a wall of high-energy particles right at the horizon that incinerates anything trying to cross. This contradicts everything we thought we knew about black holes. The equivalence principle, Einstein's foundational insight, says that free fall is indistinguishable from floating in empty space. No forces, no drama. If you're falling into a black hole, you shouldn't feel anything special at the horizon. You just cross it. The tidal forces come later, closer to the singularity, but AMP said no. If you want to preserve quantum mechanics, if you want information to escape in Hawking radiation, the horizon must be a firewall. You can't have both, smooth horizon or information preservation. Pick one. This is still being debated 12 years later, in 2024, 2025, 2026. Physicists are still arguing about it, still proposing solutions, still trying to figure out what's actually true. And the whole debate traces back to the tensions Feynman identified: quantum mechanics versus general relativity, information versus geometry. Let me explain the paradox carefully. When a black hole forms and then evaporates via Hawking radiation, we need information to be preserved. Quantum mechanics demands it. That means the information about what fell in must somehow escape in the radiation. But early Hawking radiation is emitted when the black hole is large, old, and has already swallowed lots of matter. For that early radiation to carry information about specific things that fell in, say a particular book, it must be entangled with the information inside the black hole. This is how quantum information works. Entanglement, correlations between particles. The radiation is entangled with the interior. But wait, near the horizon, there's also entanglement between particles on opposite sides. The vacuum state near horizon is entangled. That's part of what creates Hawking radiation in the first place. A particle just outside the horizon is entangled with its partner just inside. So now you have a problem. The radiation is entangled with the interior to carry information out. But the interior is also entangled with particles near the horizon because of the vacuum structure. That's too much entanglement. In quantum mechanics, there's a limit. Monogamy of entanglement. A quantum system can't be maximally entangled with two different systems at once. Something has to give. AMP said the vacuum structure at the horizon must be destroyed. Instead of a smooth, entangled vacuum, the horizon is filled with high-energy particles. A firewall. This preserves information. The radiation can carry it out, but it violates the equivalence principle. An infallen observer burns up at the horizon. This shouldn't happen. Einstein's theory says the horizon is locally just like flat space-time. Nothing special there. But quantum mechanics says otherwise. Contradiction. People have proposed solutions. Many solutions. Maybe information doesn't escape until the very end, when the black hole is tiny. Then there's no contradiction. Early radiation doesn't need to be entangled with the interior. But calculations suggest information must start escaping much earlier. The page time, when the black hole is about half evaporated. Maybe the entanglement is more subtle. Maybe there are quantum error correcting codes that allow information to be encoded redundantly. Interior and radiation both carry it. Maybe space-time itself is reconstructed from entanglement patterns. The interior and exterior aren't separate. They're different descriptions of the same quantum information. ER-EPR, Einstein-Rosen bridges equal Einstein-Podolsky-Rosen entanglement. Wormholes equal quantum entanglement. Maldacena and Susskind proposed this in 2013. Radical. Speculative, may be true. Maybe the whole notion of interior versus exterior breaks down at the quantum level. Maybe there's no firewall because there's no meaningful boundary, just quantum information in different bases. Or maybe black holes are fuzzballs. No horizon, no interior, just a quantum fuzzball of strings. String theory solution, controversial. Or maybe the equivalence principle is wrong. Maybe you do burn up at the horizon. Maybe that's just how it is. Nobody knows. The debate is ongoing. Top theorists disagree. Papers are published weekly exploring different angles. This is the cutting edge of theoretical physics right now. In 2026, and it exists because of the tensions Feynman identified 60 years ago. Quantum mechanics versus general relativity, information versus geometry. Feynman knew they didn't fit together smoothly. He didn't solve the problem, but he saw it clearly. He saw that you can't just apply quantum field theory and curved space-time naively. There are paradoxes, contradictions, breakdowns. The firewall paradox is the sharpest version of this. It forces you to choose quantum mechanics or the equivalence principle. Both can't be exactly right in the presence of a black hole. Something deeper is going on. Maybe quantum gravity resolves it. Maybe a full theory of quantum space-time eliminates the paradox. Maybe the horizon isn't a sharp surface in quantum gravity. Maybe it's fuzzy, spread out over Planck lengths, and the whole question becomes ill-defined. Maybe, we don't know. But here's what matters. Einstein never faced this paradox. He couldn't. He didn't have the framework. Feynman set up the framework. He showed that quantum mechanics matters near horizons. That information matters. That you can't just use classical general relativity. And now, 7 decades later, we're still wrestling with the consequences. The firewall paradox isn't solved, but it's well posed. We know what the question is, we know why it's hard, we know what principles are in tension. That's progress, not the answer, but the right question. And the question came from taking Feynman's approach seriously, treating black holes as quantum objects, demanding that information is preserved, insisting that quantum mechanics and gravity must be compatible, even if we don't yet know how. Einstein would have approached this differently. He might have questioned quantum mechanics, looked for hidden variables, suggested that information preservation isn't fundamental. He might have said the equivalence principle is exact and quantum mechanics needs modification. But Feynman's legacy is different. Trust quantum mechanics. It's been tested exhaustively. It's right. If it contradicts general relativity, then general relativity, or our understanding of it, needs modification, not abandonment, modification, quantum gravity, whatever that is. The firewall paradox is telling us we need it. We need a theory where quantum mechanics and gravity are unified from the start, not bolted together. Unified, string theory tries, loop quantum gravity tries, other approaches try, none are proven, none have experimental confirmation. But the paradox is a guide. It's showing us where the cracks are, where our current theories fail, where new physics must live, and that's the deepest legacy of Feynman's work on black holes. Not a solution, a methodology. When you find a paradox, don't ignore it, don't dismiss it, don't assume one side is wrong. Dig deeper. The paradox is telling you something. Einstein avoided paradoxes. He argued black holes don't form, so we don't have to worry. Feynman embraced paradoxes. He said they're where the interesting physics is, and he was right. The firewall paradox is interesting. It's deep. It's unsolved, and it's exactly the kind of problem Feynman taught us to love, the kind that breaks our current understanding and forces us to build something better. Why Einstein missed these insights? Let's be clear about something. Einstein wasn't wrong. General relativity is one of the most successful theories in the history of science. It predicts the bending of starlight, the perihelion precession of Mercury, gravitational time dilation, gravitational waves, all confirmed, all measured, all exactly as Einstein predicted. Black holes exist. We've photographed their event horizons. We've detected gravitational waves from black hole mergers. Einstein's equations describe them beautifully. So why did he miss what Feynman saw? Not because he was less intelligent. That's absurd. Einstein was arguably the greatest physicist of the 20th century, maybe of all time, but he worked in a different era, with different tools, different frameworks, different assumptions, and that made all the difference. First, timing. Einstein published general relativity in 1915. Quantum mechanics was just being born. Planck's constant was 15 years old. Bohr's model of the atom was 3 years old. The Schrödinger equation, 1926. Heisenberg's uncertainty principle, 1927. Quantum mechanics in any mature form didn't exist when Einstein was developing general relativity. By the time quantum mechanics was established, Einstein was already moving away from it. He never accepted it. The EPR paper in 1935. God does not play dice. He spent the last 30 years of his life, from 1925 to 1955, trying to replace quantum mechanics with something deterministic. Unified field theory, attempting to unify gravity and electromagnetism in a classical, geometric framework. He failed. The universe is quantum. There's no getting around it. But Einstein never stopped trying. Feynman, on the other hand, was born into the quantum era. Born in 1918, grew up with quantum mechanics already established, learned it as a student, helped build quantum field theory as a young researcher. QED in the late 1940s, Feynman diagrams, path integrals, renormalization. By the time Feynman thought about black holes in the early 1960s, quantum field theory was mature, tested, proven. He had tools Einstein never had. Second, philosophy. Einstein believed in determinism, in objective reality, in local realism. He believed that physical quantities have definite values, whether you measure them or not. He believed that causes are local. Action at a distance bothered him. Quantum mechanics violated all of this. Superposition. A particle doesn't have a definite position until you measure it. Entanglement. Measuring one particle instantly affects another, arbitrarily far away. Uncertainty. You can't know position and momentum simultaneously. Einstein found this unacceptable, not because the math was wrong, but because it violated his intuition about how nature should work. I like to think the moon is there even when I'm not looking at it. Feynman had no such hang-ups. He said, "Nature is what it is. Our intuition is wrong. Get over it." I think I can safely say that nobody understands quantum mechanics, but we can calculate with it. We can make predictions, and the predictions work. So use it. Trust it. Push it to extremes and see what happens. That's what Feynman did with black holes. He applied quantum mechanics even though it seemed absurd, even though it led to strange conclusions. Particle creation from vacuum, information paradoxes, quantum foam. He didn't reject these because they were counterintuitive. He explored them. Einstein would have rejected them, or at least been deeply skeptical. Third, observational evidence. In Einstein's lifetime, there was no evidence for black holes. None. The term didn't even exist until 1967, 12 years after he died. Cygnus X1, the first strong black hole candidate, was discovered in 1964. Quasars, powered by supermassive black holes, were discovered in 1963. Gravitational waves from black hole mergers, 2015, 60 years after Einstein's death. The Event Horizon Telescope image of M87 Xiao, 2019. Einstein never saw any of this, so from his perspective, black holes were a theoretical curiosity, a weird solution to his equations that probably doesn't occur in nature. Why spend time on them? Feynman, on the other hand, lived in an era where black holes were becoming observationally relevant. By the 1960s, astronomers were finding objects that couldn't be explained without invoking extreme gravity, X-ray binaries, active galactic nuclei, quasars. Black holes weren't just theoretical anymore, they were astrophysical. That made them worth studying. Fourth, technology. Einstein worked with pen and paper, analytical solutions, approximations. Computers didn't exist. Numerical simulations were impossible. So you could only solve simple, symmetric cases. Schwarzschild's solution, rotating black hole, Kerr solution, but not until 1963. Dynamical black holes, black hole mergers, accretion disks, too complicated. The equations couldn't be solved. Feynman had access to early computers. Caltech had computing facilities by the 1960s. People were starting to do numerical relativity, simulating gravitational systems. It was still primitive, but it was possible. And it changed what questions you could ask. You could explore scenarios that didn't have analytical solutions. You could test ideas numerically. This opened up black holes as a field of active research. Fifth, and most fundamentally, the framework. Einstein thought in terms of geometry, space-time curvature, geodesics, smooth manifolds, beautiful, elegant, powerful, but purely classical. Feynman thought in terms of quantum fields, particles, amplitudes, path integrals, also beautiful, also powerful, but fundamentally different. When you approach black holes with Einstein's framework, you see singularities, event horizons, geodesic incompleteness, problems, breakdowns, places where the theory fails. When you approach black holes with Feynman's framework, you see opportunities, places where quantum effects become important, where new physics emerges, where predictions can be tested. Neither framework is wrong, but they see different things. Einstein's framework told him to avoid black holes. They're pathological. Feynman's framework told him to study black holes. They're where quantum and gravitational effects combine. Different conclusions from different assumptions. And here's the thing. Einstein couldn't adopt Feynman's framework even if he wanted to, because that framework didn't exist yet when Einstein was at his peak. Quantum field theory was developed in the 1940s and 50s. Einstein was in his 60s and 70s by then. Working on unified field theory, isolated from the mainstream, he wasn't learning new techniques. He was pursuing his own vision. By the time Feynman was thinking about quantum gravity in the 1960s, Einstein had been dead for nearly a decade. So the question isn't, why didn't Einstein see what Feynman saw? The question is, how could he have? He lacked the tools, the framework, the observations, the computational power, and perhaps most importantly, he lacked the willingness to fully embrace quantum mechanics. That was the real barrier. Einstein could have learned quantum field theory in principle. Other physicists his age did, Pauli, Dirac, Wigner, but Einstein chose not to. He rejected it philosophically. He thought quantum mechanics was incomplete, that there must be something deeper, something deterministic underneath. He was wrong about that. Quantum mechanics is complete. Bell's theorem proved it in 1964. Experiments confirmed it. But Einstein never knew. He died believing quantum mechanics would be superseded. Feynman knew better. He helped build quantum mechanics. He saw its power, its precision, its strange, counterintuitive correctness, and he used it fearlessly. That's why Feynman saw what Einstein missed. Not greater intelligence, different tools, different era, different philosophy. Einstein built the theory that predicts black holes. Feynman built the theory that explains them. Both were necessary. Neither was sufficient alone. And that's how science progresses. Not through single geniuses solving everything, but through generations building on each other. Einstein laid the foundation, general relativity, space-time curvature, black hole solutions. Feynman added the quantum structure, particle creation, information, thermodynamics. Hawking combined them. Calculated radiation, proved black holes evaporate. Modern physicists push further. Holography, firewalls, quantum gravity. Each generation sees further. Not because they're smarter, but because they're standing on the shoulders of those who came before. Einstein couldn't see what Feynman saw because Feynman was standing on Einstein's shoulders, looking from a higher vantage point with better tools, clearer vision. That's the beauty of science. It's cumulative, collaborative across time. Einstein wasn't wrong. He just wasn't complete, and he knew it. Toward the end of his life, he said, "I have made one great mistake in my life. When I signed the letter to President Roosevelt recommending that atom bombs be made." But scientifically, his mistake was subtler. Not rejecting general relativity, that was right, but rejecting quantum mechanics. That was the missed opportunity. If Einstein had embraced quantum mechanics instead of fighting it, he might have seen what Feynman saw. He might have asked, what happens quantum mechanically near an event horizon? He might have anticipated Hawking radiation, holography, information paradoxes, but he didn't. He couldn't. His worldview wouldn't allow it. And so those discoveries fell to others, to Feynman, to Hawking, to the generations that followed. That's not a failure. That's how science works. No one sees everything. No one can. We each contribute our piece, our perspective, our insight, and together across decades and centuries, we build understanding. Einstein gave us black holes, the geometry, the equations, the predictions. Feynman gave us the quantum key, the framework to unlock what black holes really are. And we're still turning that key, still discovering what lies beyond the horizon, still unraveling the quantum structure of space-time itself. That's Einstein's and Feynman's legacy, not individual discoveries, but the foundation for everything that came after. The revolution is still ongoing. The avalanche, as the original script said, is still avalanching along at high speed, and we're part of it, standing on the shoulders of giants, seeing further than they could, because they showed us where to look.